Hello, and welcome back to this quiet corner of the universe. Take a moment, if you will, to listen to the sound of the rain outside your window, if it happens to be raining. Think of the rhythm of it, the scent of wet earth, the way it seems to wash the world clean. Rain is a promise of life, a cycle of renewal. But what if that cycle broke? What if the promise was not of a passing shower, but of a deluge that lasted longer than our species has existed? Tonight, let us wonder together about a lost world, a time when it rained for 2 million years straight. It's hard to imagine a world so drenched, a sky so endlessly gray. But the story is written in the ancient stones of our planet, waiting to be read. If you find this journey suits you, a like or subscribe helps this small signal find other curious minds. There is, of course, no pressure at all. I'm always curious to know where on this planet you are listening from and what time it is in your part of the world. It's a wonderful thought that we, separated by space and time, can share this moment together. Now, find a comfortable position and let your mind slow to the rhythm of time. Our journey begins. Our story does not start with the rain, but with the profound dryness that came before it. Let us travel back in time, not just a few thousand years, but 234 million years, into a period known as the Triassic. From a quiet vantage point in space, our Earth would be almost unrecognizable. The familiar blues and greens are there, but the arrangement is all wrong. There is no Atlantic Ocean, no graceful curve of Africa, no distinct Americas. Instead, there is one colossal ocean, Panthalassa, a single body of water covering nearly 70% of the globe. And adrift in this immense sea is a single lonely landmass, the supercontinent of Pangaea. It is a world of immense scale and stark simplicity. Pangaea is shaped like a giant letter C, cupping a smaller wedge-shaped body of water called the Tethys Sea. This is the planet's architecture, a global puzzle of all the major continental plates locked together. The land that will one day become North America is fused to what will be Europe and Asia. South America is nestled against Africa, which in turn is connected to Antarctica, Australia, and India. It is a world without the familiar separations we know today. A world where a creature could, in theory, walk from the South Pole to the North Pole without ever crossing a major ocean. This grand consolidation of land was the result of geological forces playing out over hundreds of millions of years. Continents, moving at the pace of a growing fingernail, had slowly drifted, collided, and sutured themselves together, crumpling their edges to form immense mountain ranges, some of which may have dwarfed our modern Himalayas. The reasons for this grand cyclical assembly of supercontinents remain one of the deepest mysteries in geology. A planetary rhythm, a slow heartbeat of stone whose ultimate cause is still debated. It is as if the Earth itself breathes, gathering its landmasses together for an eon, only to exhale and send them flying apart once more. Let us drift closer now, through the thin upper atmosphere of this Triassic world. The air is different here. Oxygen levels are lower than they are today, perhaps only 16% compared to our 21%, making the air feel thin, almost alpine, but it is thick with other gases. Carbon dioxide levels are perhaps 5 times higher than they are in our modern pre-industrial world. This creates a potent greenhouse effect, trapping the energy of a sun that was, paradoxically, slightly younger and dimmer than the one we know. The world below is therefore a hot one, a planet living in a permanent state of fever. The defining feature of Pangaea is its sheer size. The continent is so vast that most of its interior lies thousands of kilometers from the ocean. The moisture-laden winds that blow from the sea rarely penetrate this deep continental heartland. As a result, the center of Pangaea is a desert of unimaginable scale. Imagine a desert larger than the entire continent of Africa, a sea of red sand and rock baking under the Triassic sun. There are no grasses here. They have not yet evolved. There are no flowering plants. The The vegetation where it exists is alien. Hardy seed ferns, towering cycads that resemble squat palm trees, and strange, woody lycopods. This is a world of extreme climates. The immense landmass heats up and cools down far more dramatically than our scattered modern continents. The winters are brutally cold and dark, while the summers are scorchingly hot and long. This temperature difference creates a weather system of planetary proportions. The Pangean mega-monsoon. For part of the year, colossal high-pressure systems build over the cold interior, pushing dry air outwards. For the other part of the year, the sun-baked land creates a vast low-pressure zone, which pulls in immense amounts of moisture from the Panthalassic Ocean and the Tethys Sea, resulting in seasonal rains of incredible violence around the continent's coasts. But deep within, the rain rarely falls. The heart of Pangaea is a world defined by its thirst. This was the stage. A single unified continent of vast arid plains and scorching deserts, fringed by coastlines that pulsed with seasonal monsoons. Life was clinging on, recovering from a devastation that had come before, an extinction so profound it had nearly extinguished the flame of complex life on Earth entirely. The world was stable, in a harsh and brittle sort of way. It was a world of red earth and a pale sun, waiting for a change, waiting for a trigger that would push its already extreme climate over a hidden threshold and begin a chapter of planetary history so wet it is almost beyond our comprehension. It was waiting for the first drops of a rain that would not end. To understand this dry Triassic world, we must first understand the silence that haunts it. The stillness in the air is not the peace of an ancient, untouched paradise. It is the quiet of a world recovering from a near-total collapse. The arid stability we spoke of was built upon the ruins of a former far richer world. For just 17 million years before our story begins, a mere heartbeat in geological time, life on Earth had nearly been extinguished. This event, known as the Permian-Triassic extinction, or more simply, the Great Dying, was the single greatest catastrophe life has ever endured. It is difficult for us to grasp the scale of this loss. It was an apocalypse that unfolded not over days or weeks, but over millennia, driven by forces from deep within the planet. The leading suspect, according to the story told in The Rock, was a volcanic event of unimaginable proportions in what is now Siberia. For hundreds of thousands of years, fissures in the Earth's crust bled lava, covering an area larger than modern Europe, with molten rock thousands of meters thick. But the lava was not the true agent of destruction. The volcanoes released biblical quantities of carbon dioxide, methane, and sulfur into the atmosphere, triggering a runaway greenhouse effect. The planet's temperature soared. The oceans absorbing the heat and carbon dioxide became acidic and starved of oxygen, turning into vast, stagnant dead zones. On land, acid rain stripped the soils and poisoned the plants. The intricate web of life, woven together over 300 million years, simply unraveled. When the dust and gases settled, the planet was eerily empty. It is estimated that 96% of all marine species vanished. In the seas, the great trilobites, constants of the Paleozoic era, were gone forever. The vast, intricate reefs of ancient corals and sponges collapsed into rubble. On land, more than 70% of vertebrate species disappeared. The great forests of giant club mosses and ferns died, leaving a world scoured by erosion, a planet of mud and fungi. Life had come so perilously close to the brink that for a time it seemed the entire experiment of complex life might fail. The mystery of the Great Dying is not just what caused it, but how anything survived at all. And it is in the nature of these survivors that we can understand the world of the Triassic. The aftermath of the extinction was not a sudden explosion of new and wonderful creatures. It was a long, bleak period known as the disaster interval. The world was inherited by the hardy, the simple, and the opportunistic. For millions of years, the terrestrial world was dominated by a single kind of animal, a creature called Lystrosaurus. It was not a fearsome predator or a majestic giant. It was a squat, pig-sized herbivore with a beaked face and 2 tusks. It was a burrower, a generalist, a creature that could seemingly eat whatever tough, scrubby vegetation survived, and could weather the harsh climate by digging into the earth. For a time in the early Triassic, Lystrosaurus accounted for as much as 90% of all land vertebrates on the planet. From the southern plains of Pangaea to the northern coasts, the world belonged to this humble, persistent survivor. The oceans told a similar story. The first reefs to reappear were not built of coral, but of masses of microbes. The first common shellfish was a small, unremarkable bivalve named Claria. These were the disaster taxa, the weeds in a garden that has been burned to the soil. They were not complex or specialized, but they were resilient. They were the placeholders, the pioneers, reseeding a desolate world. Our story, set 17 million years after the peak of the dying, takes place in a world that has made significant progress in its healing. Lystrosaurus is gone, having given way to a greater diversity of life. The ecosystems are more complex than they were in the immediate aftermath, but the ghost of the extinction remains. The planet's biodiversity is still a shadow of what it was before the Permian. Entire classes of animals and plants are simply gone, leaving vacant roles in the ecosystem that are only now, slowly, beginning to be filled by new experiments in evolution. This long shadow of devastation is crucial to our story. It means the world on the eve of the Great Rains was not a robust, stable system. It was a world of survivors, a world of lineages that had passed through the eye of a needle. The creatures inhabiting this hot, dry Pangaea were the descendants of those who had endured the unendurable. They were predisposed, perhaps, to toughness, but they had recovered in a world of extremes, a world that was already teetering on a climatic knife's edge. They did not know that the forces that had nearly ended their world once before, colossal volcanism and a poisoned sky, were gathering strength again. The planet's great fever had broken, but it was about to return in a different form, not as a planet of fire, but as a planet of water. Into this recovering world, this ghost of a world, stepped a new dynasty. The Great Dying had scoured the planet, leaving countless ecological roles vacant. It was a planetary-scale job interview, and the group of animals that seemed most poised for success were the reptiles. And among the reptiles, one group in particular radiated with evolutionary vigor: the archosaurs, the ruling reptiles. They were the great experiment of the Triassic period. From this single ancestral stock, 2 profoundly different paths were taken, 2 competing designs for how to conquer a continent. The first branch was the Pseudosuchia, a name that means false crocodiles. This is the lineage that would eventually lead to our modern crocodilians. But in the Triassic, they were far more diverse and dominant than their semi-aquatic descendants. They were the undisputed masters of Pseudosuchia. The second branch was the Avametatarsalia, the bird ankles, which would give rise to the pterosaurs, the dinosaurs, and eventually the birds themselves. In our own time, the bird lineage is immensely successful, with thousands of species. But back in the mid-Triassic, on the arid plains of Pangaea, the world belonged to the false crocodiles. To walk across the heartland of Pangaea before the rains was to walk through their kingdom. The apex predator was not a dinosaur. It was likely a Rauisuchian, a creature like Postosuchus. Imagine a 15-foot-long predator built like a crocodile, but with long pillar-like legs held directly beneath its body, allowing it to move with a terrifying efficiency across the dry landscape. With a massive skull full of blade-like teeth, it was the Triassic equivalent of a lion or a grizzly bear, a formidable hunter at the top of the food chain. These were not slow, sprawling creatures. They were active, powerful predators that stalked the land. The role of the large, sturdy herbivore was not filled by a creature like Triceratops or Stegosaurus. Instead, there were the Eidosaurs. Picture a creature like Desmatosuchus, a heavily armored, pig-like reptile covered from snout to tail in a mosaic of bony plates or osteoderms. Some, like Desmatosuchus, even had great defensive spikes curving out from their shoulders. They were walking fortresses, shuffling through the tough vegetation, their armor a testament to the dangerous world they inhabited. They were the tanks of the Triassic, relying on passive defense to survive in a world of powerful predators. In the rivers and lakes that fringed the Great Desert, another member of this dynasty held sway, the phytosaurs. At first glance, you would mistake one for a modern crocodile or gharial. They had the same long snout, the same powerful tail for swimming, the same lifestyle of a patient, semi-aquatic ambush predator. But a subtle clue gives them away as a remarkable case of convergent evolution. A true crocodile has its nostrils at the tip of its snout, allowing it to breathe while almost fully submerged. A phytosaur's nostrils were located on a raised mound of bone just in front of its eyes. It is a small difference, but one that speaks to a separate evolutionary journey, a different answer to the same question of how to hunt in the water. This was the established order, a world ruled by a diverse and successful cast of crocodile line archosaurs. So where in this grand theater were the dinosaurs? They were there, but they were not the stars of the show. They were small players living in the margins. The first dinosaurs, creatures like Eoraptor, were no larger than a dog. They were nimble, bipedal animals, likely scurrying through the undergrowth, hunting insects and small vertebrates, and doing their best to stay out of the way of the much larger Rauisuchians. For millions of years, they were a minor part of the global fauna, an evolutionary experiment that showed promise but had not yet found its moment. The key difference between these two great archosaur branches, the source of their different destinies, may have been hidden in their ankles. The crocodile line archosaurs had a flexible, rotating ankle joint, the crurotarsal ankle. It allowed their feet to sprawl, a versatile tool for walking and swimming. The dinosaurs and their kin, however, had evolved a simpler, more efficient joint, the mesotarsal ankle, which acted as a straight hinge. This design was less flexible, but it was perfect for fast, efficient, straight-line running. It was an ankle built for endurance. Scientists still wonder why this seemingly minor detail may have been so important. For millions of years, the flexible ankle of the crocodile relatives was part of a winning formula. Their members were bigger, more diverse, and more dominant. Yet history tells us that a great reversal of fortunes was coming. The small bipedal dinosaurs, with their efficient, hinge-like ankles, were poised on the edge of greatness. They were waiting for the world to change, for the established order to be thrown into chaos. They did not know it, but the coming storm, the 2-million-year reign, would test both of these evolutionary designs to their absolute limit. The world before the reign belonged to the cousins of crocodiles, but the world after would be a very different place. Let us leave the dusty red plains of the archosaurs and walk towards the coast. Here, the immense arid silence of inner Pangaea gives way to the sound of waves. Before us lies the greatest ocean the world has ever known, Panthalassa, a seemingly endless expanse of blue water. And nestled in the great curve of the supercontinent is the Tethys Sea, a vast tropical gulf whose warm, shallow waters would, in a future age, leave their mark on the lands from the Alps to the Himalayas and even to the shores of Southeast Asia. Like the land, this global ocean was a world in recovery. The Great Dying had been even more thorough in the seas, and for millions of years, the waters were stagnant, acidic, and largely empty. In the immediate aftermath, a strange phenomenon known as the Lilliput effect took hold. The few species that survived were noticeably smaller than their ancestors, a sign of a stressed ecosystem struggling to rebuild. But by the time our story begins, 17 million years later, the oceans were once again teeming with life, and the most remarkable pioneers of this new marine world were, once again, the reptiles. Having conquered the land, several lineages felt the evolutionary pull of the water and began a journey back into the ancestral home of all vertebrates. This was the first great age of marine reptiles. In the shallow coastal lagoons, you would find the placodonts. These were heavily built, almost clumsy-looking reptiles. Some, like Placotus, looked like stout, barrel-chested iguanas, while others, like Henodus, had flattened bodies and shells that made them look remarkably like turtles. Their defining feature was their teeth. Their front teeth were peg-like, perfect for plucking shellfish from the seabed, while their broad, flat teeth in the back of their jaws formed powerful crushing plates. They were the slow-moving bottom feeders of the Triassic, the sea walruses of their time, content to graze on the abundant clams and brachiopods. Further out from shore in the sunlit waters were the nothosaurs. These creatures represent a perfect intermediate step between a life on land and a life at sea. With bodies like a large lizard, a long and flexible neck, and a skull full of needle-sharp teeth for catching fish, they were formidable hunters. Their limbs, however, were not yet fully committed to the water. Instead of true flippers, they had webbed feet, suggesting they were powerful swimmers but could also haul themselves out onto rocks or beaches, much like a modern seal. They were amphibious predators, bridging two worlds, hunting in the sea but perhaps still tied to the land for rest and to lay their eggs. But the true masters of the Triassic seas were the ichthyosaurs, the fish lizards. Unlike the placodonts and nothosaurs, they had severed all ties to the land. They appeared in the fossil record with a suddenness that still puzzles paleontologists. Their direct land-dwelling ancestors remain a mystery, as the earliest known ichthyosaurs were already supremely adapted to marine life. They had streamlined, dolphin-shaped bodies, powerful crescent-shaped tails that beat side to side like a fish, and forelimbs and hindlimbs that had been completely transformed into steering fins. Their most striking feature was their enormous eyes, some of the largest relative to body size of any animal that has ever lived. These huge eyes suggest they were deep divers, hunting for squid and fish in the dim light far below the surface. They did not lay eggs on land. They gave birth to live young at sea, fully independent of the terrestrial world. They were the Triassic blueprint for a successful ocean predator, an evolutionary design so perfect that it would be echoed much later by the dolphins and whales. While these new predators ruled the water column, a quiet revolution was taking place on the seafloor. The ancient reefs, built by extinct forms of coral and sponge, were gone. In their place, a new kind of builder was emerging, the scleractinian corals. These are the ancestors of every coral that builds the great reefs of our modern world. In the Triassic, their efforts were small, tentative. They formed fragile, patchy reefs in the warm waters of the Tethys, nothing like the Great Barrier Reef of today. But it was a start. These new corals were creating the architecture for a new kind of marine ecosystem, fragile cities of stone that provided shelter for countless other creatures. And so, the picture of our world before the rain becomes more complete. It was a planet of two realms, both shaped by recovery and innovation. On the single great landmass, the diverse cousins of crocodiles reigned supreme, while the first small dinosaurs scurried in their shadows. And in the single great ocean, the first wave of marine reptiles staked their claim, while the first modern corals began their patient, eons-long work of building a new world beneath the waves. The entire planet was a theater of new life, a vibrant but fragile system, unaware that the rules of existence were about to be rewritten by a change in the sky. The creatures of the land and the creatures of the sea, from the mightiest Rauisuchian to the smallest coral, all lived their lives subject to the rhythm of a planetary machine. The Triassic climate, and the climate of a world with one supercontinent and one superocean, was unlike anything we experience today. It was a climate of absolutes, of brutal simplicity and extraordinary power, all driven by a phenomenon known as continentality. Land, as we know, heats up and cools down much more quickly than water. An ocean is a great moderator, a thermal battery that absorbs the sun's heat and releases it slowly. Pangaea had almost no large inland seas to moderate its temperature. It was an uninterrupted mass of rock and soil stretching nearly from pole to pole. This created a weather engine of immense proportions, a mega-monsoon that was the true ruler of the Triassic world. For many of us who live in the tropical parts of the world today, the monsoon is a familiar rhythm, a life-giving shift in the winds that separates the dry season from the wet. But the Pangaean monsoon was of a different order of magnitude entirely. It was a planetary scale breath, drawn in and exhaled once a year. Let us imagine the Pangaean winter in one hemisphere. With the sun low in the sky, the vast continental interior, thousands of kilometers from the ocean's warmth, would grow intensely cold. This immense region of cold land would chill the air above it, creating a colossal continent-sized dome of dense, high-pressure air. This was the planet's great exhale. From the center of Pangaea, dry, frigid winds would rush outwards towards the coasts, pushing the moisture of the sea away. For half the year, much of the supercontinent would be locked in a profound, wind-swept drought. Then the seasons would turn. The sun would climb higher in the sky, its energy beating down upon the exposed rock and red soil of the interior. The land would heat up relentlessly, becoming a planetary-scale furnace. This vast expanse of hot land would heat the air above it, causing it to rise and creating an enormous, continent-spanning zone of low pressure. This was the planet's great inhale. The low pressure in the interior acted like a vacuum, pulling in the warm, wet, humid air from the Panthalassic Ocean and the Tethys Sea. This moist air, once it reached the hot landmass, would rise, cool, and condense, unleashing rains of unimaginable intensity. The coasts of Pangaea would be battered by months of torrential downpours, transforming the landscape into a world of swollen rivers, vast floodplains, and lush, swampy wetlands. It is in these coastal regions that we find the geological evidence of this wet season. The great coal deposits of the Triassic. Coal is the remnant of countless generations of plants that grew in ancient, waterlogged swamps. Its presence along the ancient Pangaean coastline is a clear fingerprint of this yearly deluge. But the monsoon's reach was limited. The sheer size of Pangaea meant that this ocean moisture could only penetrate so far. The deep interior remained a desert. We find the evidence for this too, written in the stone. Here, we find vast evaporate deposits, thick layers of salt and gypsum. These are the mineral ghosts of ephemeral seasonal lakes that would form briefly before evaporating entirely under the scorching summer sun, leaving their dissolved minerals behind. A world of swamps on the edge, and a world of salt pans at the heart. This was the rhythm of Triassic life, a harsh, predictable cycle of extreme drought followed by extreme rain. The plants and animals were adapted to this cycle. They knew how to endure the long dry season and how to take advantage of the sudden, life-giving abundance of the wet. For millions of years, this planetary heartbeat was the background noise of existence. But scientists who modeled this ancient climate in computers wondered just how stable this system truly was. Was it a perfect, unwavering clock? Or was it a system under such extreme tension that it was prone to chaotic behavior, a powerful engine that was, perhaps, dangerously sensitive? It was a system in a delicate dynamic balance, a balance between the heat capacity of the land and the sea, a balance between evaporation and precipitation, a balance of atmospheric gases that determined just how much heat the planet held onto. For millions of years, the engine ran smoothly, driving the seasons of life on the lonely supercontinent. But it was a machine that could be broken. It only needed a sufficient shock, a powerful enough push, to jam the gears. The great inhale could be forced to continue, the torrential rains not ceasing after a few months, but continuing, season after season, year after year, until the distinction between wet and dry was lost, and there was only the rain. The shock that would jam the gears of the great Pangaean monsoon came not from the sun or the sky, but from the deep, silent furnace of the Earth's interior. The very existence of a supercontinent, like Pangaea, carries the seeds of its own destruction. By assembling all the land into one place, the continental crust acts like a giant insulating blanket, trapping the immense heat that flows upwards from the planet's core. Beneath this blanket, the mantle grows hotter and hotter, its slow churning currents of rock becoming more vigorous, pushing upwards against the underside of the continental plate, searching for a way to release the strain. A supercontinent cannot last forever. It is an inherently unstable arrangement in the long story of a planet. To find the source of the coming change, we must leave the surface world behind. We travel down through the red desert soils, through kilometers of ancient sedimentary rock, and into the crust itself. We continue deeper, past the boundary where the crust gives way to the mantle, a vast layer of solid rock that flows like thick honey over geological timescales. The pressure is immense. The heat is unimaginable. Here, in this slow-motion ocean of rock, the fates of the continents are decided. For millions of years, forces had been building against Pangaea. In the great Panthalassic Ocean to the west of the supercontinent, the heavy oceanic crust was being forced underneath the lighter continental crust of Pangaea. This process, known as subduction, is a primary engine of tectonics. It is a slow, grinding collision of plates that generates earthquakes, lifts mountain ranges, and creates immense reservoirs of molten rock, or magma, deep underground. The western edge of Pangaea, a region that would one day become the west coast of North America, was one such subduction zone. It was a place of geological tension, a seam where the supercontinent was being actively squeezed and deformed. It was a weak point. And deep beneath this weak point, another force may have been rising. From the boundary of the liquid outer core itself, some 2,900 kilometers below the surface, a plume of unusually hot mantle rock may have begun its slow ascent. Imagine a bubble rising in a thick liquid, a journey that takes millions of years. This is a mantle plume, a colossal upwelling that acts like a blowtorch on the underside of a tectonic plate. When such a plume reaches the base of the crust, it can spread out, doming the land upwards, stretching it and thinning it from below. Here lies a great geological mystery, a chicken and the egg question. What was the ultimate cause of the cataclysm to come? Was it the long, slow tension of subduction and the internal stresses of a continent beginning to pull itself apart? Or was it the arrival of a deep mantle plume, a targeted blast of heat from the planet's heart that exploited an existing weakness in the crust? Scientists still debate the precise sequence of events. Perhaps the two forces were linked, part of the same grand planetary process that sees continents gather and disperse. What we do know is that in this specific region of western Pangaea, the crust was being strained to its breaking point. The archosaurs hunting on the plains and the ichthyosaurs gliding through the Tethys Sea were blissfully unaware of these colossal forces building beneath them. The life of the Triassic was conducted on a thin, fragile shell, a crust of rock floating on a sea of fire. The deep groans of the planet were inaudible on the surface, but the pressure was mounting. In the deep, magma chambers were growing, swelling with molten rock and superheated gas. The great continental plate, which had been fused together for 100 million years, was beginning to strain. The cracks were beginning to show. It is a profound thought that the geography of our modern world, the existence of the very ground beneath our feet, is a direct consequence of these ancient strains. The tension that would eventually rip Pangaea apart and open the Atlantic Ocean, the forces that would push India into Asia and raise the Himalayas, the process that would shape the Pacific Ring of Fire and the quiet seas of Southeast Asia. It all began here as imperceptible stresses in the rock, the first hints of a breakup. The world was poised for a profound geological shift. The first and most violent expression of this shift would not be the movement of continents, but an eruption of fire and gas that would fundamentally alter the climate of the entire planet and bring on the rain. The breaking point was finally reached. The immense, patient pressure that had been building for millions of years in the deep crust and upper mantle of western Pangaea could no longer be contained. The rock, stretched and thinned from below, finally tore open. This was not the eruption of a single cone-shaped mountain. This was an event of a completely different nature and scale. This was the birth of a large igneous province. Geologists have given it a name, taken from the mountains in modern-day Alaska, where its thickest layers are now found, the Wrangellia Province. A large igneous province, or LIP, is one of the most profound expressions of a planet's inner energy. It is not a volcano in the way we usually imagine it. There is no majestic snow-capped peak. Instead, we must picture immense cracks in the earth, fissures hundreds of kilometers long, splitting the continental crust. From these fissures, lava does not explode violently into the sky, it floods. It pours out in an immense, silent, relentless deluge of molten rock. The lava is basaltic, meaning it is low in silica and very fluid, with a consistency like hot syrup. It flows easily, spreading out across the landscape in vast, flat sheets, paving over everything in its path. Let us try to picture the scene. In the far west of the supercontinent, the ground trembles and splits. A glowing red line appears on the horizon, widening into a river of fire. But this river has no banks. It is a tide of molten stone, advancing at the pace of a slow walk, but it is unstoppable. It consumes the sparse Triassic forests of cycads and ferns, not with a roar, but with a quiet, searing hiss. It fills valleys, diverts rivers, and builds up, layer by layer, a new landscape of black volcanic rock. And this is not happening in one location, but along a chain of fissures stretching for more than 2,000 kilometers from what is now central Alaska down through modern-day British Columbia. To give a sense of the scale, the total area eventually covered by this lava would be comparable to the size of the entire country of Vietnam or the state of Texas. Much of this eruption occurred not on dry land, but on the submerged continental shelf beneath the shallow waters of the Panthalassic coast. Here, the spectacle was even more dramatic. Molten rock, at over 1,000 degrees Celsius, met the cold ocean water. The result was a colossal explosion of steam, a continuous roar as uncountable tons of seawater were instantly vaporized and shot into the atmosphere. Under the waves, the lava cooled rapidly, its outer skin hardening while the inside was still molten, creating strange, rounded, pillow-like shapes. These pillow basalts are the enduring geological signature of an underwater eruption, silent witnesses to a time when the sea itself boiled. The mystery of this great outpouring lies in its timing. This was not a singular event that lasted for a week or a month. The evidence in the rock layers suggests the Wrangellia eruptions occurred over a period of 5 to 6 million years. The great question for geologists is whether this was a slow, continuous bleed of lava, or if it occurred in a series of distinct, cataclysmic pulses. By carefully analyzing the chemistry of the different lava flows, scientists try to piece together this history to understand the rhythm of the eruption. Did the planet release its energy in a few great heaves, or was it a long, drawn-out sigh? The answer has profound implications for how quickly the climate was thrown into chaos. For any creature living in western Pangaea, it would have been a localized apocalypse, a world being unmade and remade by fire. But for the vast majority of life on the supercontinent, thousands of kilometers away, it would have been a distant, unseen event. An archosaur hunting on the plains of central Pangaea would have noticed nothing, felt nothing. The ground beneath its feet would have been still. Yet its fate, and the fate of every living thing on the planet, was being sealed by this distant fire. For the true impact of a large igneous province is not the lava itself. The lava is a regional affair. The real agent of global change is invisible. It is the colossal volume of volcanic gases released from this open wound in the planet's crust, which now began to pour, unabated, into the sky. The age of fire had begun, And it would be the catalyst for the coming age of water. The lava that paved over western Pangaea was merely the body of the catastrophe. Its soul, its true global influence, was in the gases that escaped with it. We must imagine magma deep within the earth as being like a bottle of a carbonated drink. It contains vast quantities of dissolved gases, kept in solution by the immense pressure of the overlying rock. When a fissure opens to the surface, the pressure is released and these gases effervesce, escaping into the atmosphere in unimaginable volumes. For hundreds of thousands of years, the Rangelia eruptions were a slow-motion, planetary-scale exhalation. The most significant of these gases was carbon dioxide. To the creatures of the Triassic, it was invisible, odorless, and harmless to breathe at these concentrations. But in the delicate physics of a planet's atmosphere, it is one of the most powerful molecules that exists. Our Earth maintains its temperature through a fragile, beautiful balance. Energy arrives from the sun in the form of visible light, warming the land and the sea. The planet then radiates this energy back out towards space in the form of infrared heat. Some gases in our atmosphere, like oxygen and nitrogen, are transparent to this outgoing heat. But greenhouse gases, like carbon dioxide, are different. They are like a one-way gate. They let the sunlight in, but they absorb the outgoing infrared radiation, trapping the heat and warming the atmosphere. This greenhouse effect is not inherently a bad thing. It is essential for life. Without its natural carbon dioxide blanket, the Earth would be a frozen, lifeless ice ball. But the Rangelia eruptions were not part of this natural balance. They were an immense external shock to the system, a sudden thickening of the planetary blanket. Year after year, century after century, the fissures in western Pangaea pumped carbon dioxide into the sky, and the concentration of this heat-trapping gas began to rise. But the gases from the magma were only part of the story. The true power of this event came from a colossal amplifying effect. The crust of western Pangaea, where the eruptions were taking place, was not made of inert rock. It was rich with the accumulated carbon of previous ages. There were vast deposits of limestone, rock formed from the calcium carbonate shells of countless marine organisms that had lived and died over hundreds of millions of years. There were also thick seams of coal and oil shale, the fossilized remains of ancient forests and plankton blooms. As the colossal volumes of magma, at over 1,000 degrees Celsius, rose through the crust, they didn't just erupt, they cooked the surrounding rock. This planetary-scale baking process, called contact metamorphism, vaporized the ancient carbon stored in the limestone and coal, releasing it into the atmosphere as a secondary, and perhaps even larger, wave of carbon dioxide and methane. The eruptions had found a vast buried fuel source and set it alight. Scientists still work to understand the sheer quantity of carbon released. It is a great puzzle. By measuring the immense volume of the Rangelia lava flows and estimating the gas content of the original magma, they can create a baseline. But the added contribution from the burned carbon in the crust is a huge variable, a mystery that makes the numbers uncertain. The most conservative estimates suggest the event released enough carbon to double the atmospheric CO2 levels of the time. More extreme estimates suggest it could have quadrupled them, or even more. The effect on the planet was not instantaneous. It was a slow, creeping fever. An archosaur living through the first few centuries of the eruptions would have noticed no difference. The seasons would have turned as they always had. But the global energy budget had been altered. More heat was now being trapped than was escaping. The average global temperature began a slow, inexorable climb. The glaciers at the high-altitude poles, which may have existed even in the hot Triassic, would have begun to melt. The great deserts of central Pangaea would have grown even hotter. And most importantly, the single greatest reservoir of heat on the planet, the Panthalassic Ocean, began to warm. The surface waters, absorbing the atmospheric heat, would have slowly risen in temperature degree by degree. Warmer water evaporates more easily. The air above the oceans would have become laden with more and more moisture. The world was not just getting hotter, it was becoming more humid. The finely tuned engine of the Pangean megamonsoon, which relied on specific temperature differences between land and sea, was now being supercharged. The system was being loaded with heat and humidity, primed for a change that would alter the face of the entire planet. The slow fever of the planet, driven by the ceaseless output of the Rangelia volcanoes, now began to trigger a powerful secondary effect. The relationship between temperature and water is one of the fundamental laws of atmospheric physics. A warmer atmosphere can hold significantly more moisture. For every degree Celsius the air warms, its capacity to hold water vapor increases by about 7%. This is not a linear relationship. It is an exponential. As the Triassic world heated up by several degrees, its atmosphere did not just become a little damper, it became a global steam bath. The great Panthalassic Ocean, its surface warmed by the thickened greenhouse blanket, was now evaporating at a tremendous rate. Trillions of tons of water were being lifted into the sky, but instead of falling as seasonal rain, this moisture was being held in the superheated air. This was the beginning of the Carnian pluvial episode's first phase, the humid pulse. For those of us who know the feeling of a truly humid evening, where the air itself feels thick and heavy with unspoken rain, we can perhaps imagine a shadow of what this world was like. But this was a humidity of a different order, a planetary condition. The air would have been perpetually damp, heavy, and oppressive. Mists would have carpeted the lowlands, refusing to burn off even at midday. The sky would have lost its crisp, dry clarity, transforming into a permanent, milky white haze that diffused the sunlight and trapped the heat. Nights would have offered little relief, as the water vapor in the atmosphere would have trapped the day's warmth, preventing the land from cooling. This dramatic shift is not just a theoretical consequence of climate models. It is written clearly in the geological record. One of the most elegant forms of evidence comes from the microscopic world of fossilized pollen and spores. These tiny resilient grains are a planetary diary, a record of the vegetation that grew in a particular place and time. As geologists examine the rock layers from just before our story begins, they find an abundance of pollen from plants adapted to arid conditions, such as the hardy conifers. Then, in a geological instant, this signal changes dramatically. The conifer pollen all but vanishes, and in its place, there is an explosion of spores from ferns and other plants that thrive in damp, waterlogged soil. This shift, found in ancient rocks all over the world, is the unmistakable footprint of the humid pulse. The world's flora was responding in unison to a sudden global shift from dry to wet. Other clues lie in the ancient soils, which are sometimes preserved as rock layers called paleosols. The desert soils of the earlier Triassic, characterized by minerals that form in arid conditions, give way abruptly to soils rich in clays and organic matter, soils that could only have formed in a bog or a swamp. The land itself was becoming saturated. The precise nature of this transition remains a subject of scientific curiosity. When we look at the rock record, which compresses millions of years into meters of stone, did this humid pulse arrive as a single, overwhelming wave? Or did the climate system flicker, oscillating between the old, dry world and the new, wet one for a few millennia before finally tipping over? The evidence is ambiguous. Different locations seem to tell slightly different stories, a reminder that we are trying to read a complex narrative from a weathered and incomplete text. What is certain is that this atmospheric moisture created a powerful feedback loop. Water vapor is itself a potent greenhouse gas, so the initial warming caused by the volcanic carbon dioxide led to more water vapor in the atmosphere. This water vapor then trapped even more heat, which in turn caused even more evaporation from the oceans. The planet had begun a process of warming itself. The stable, predictable engine of the Pangean megamonsoon was now broken, overwhelmed by the sheer thermal energy and moisture content of the atmosphere. The old rules no longer applied. The air was now saturated, the planetary sponge soaked to its absolute limit. It was holding a colossal burden of water, an ocean suspended in the sky. The world was poised on a precipice, holding its breath. The heat was immense, the air thick and still. Every living thing, from the archosaurs on the plains to the new corals in the Tethys Sea, was now living inside a planetary pressure cooker, waiting for it to release. It would only take the slightest nudge, the smallest change in temperature or pressure, to cause this suspended ocean to fall. And then it happened. The moment the world tipped, the precise trigger, the final nudge that pushed the overloaded climate system over the edge, remains a mystery lost to time. Perhaps it was a subtle shift in the Earth's orbit, a gentle wobble that fractionally cooled a part of the atmosphere. Perhaps it was a particularly violent pulse from the Rangelia volcanoes, which threw a vast plume of ash and sulfur dioxide high into the stratosphere, creating a temporary, shadowy veil that cooled the air beneath it. Or perhaps there was no single trigger at all, simply the moment when a system under unbearable tension finally reached its inevitable breaking point. What we do know is that for rain to form, even in the most saturated sky, water vapor needs a seed. It needs a microscopic particle upon which to condense. A speck of dust, a crystal of sea salt, or a particle of volcanic ash. In the hazy choked sky of the late Triassic, these condensation nuclei were abundant. The same volcanoes that were loading the atmosphere with heat-trapping gases were also supplying the very seeds required to bring that moisture crashing back down. The system had created both the potential for the flood and the mechanism to unleash it. Let us imagine a single particle of ash drifting high in the hazy, humid air. Water molecules, energized by the planet's heat, are moving chaotically all around it. One molecule collides with the ash and clings to it, then another, and another. A microscopic droplet begins to form, a tiny sphere of liquid water where moments before there was only vapor. It grows molecule by molecule, coalescing with other droplets until it becomes heavy. Heavy enough that the lift from the air currents can no longer support it. Heavy enough that the simple, undeniable force of gravity takes hold. And it begins to fall. This single drop is joined by a billion others, then a trillion. Across a region of Pangaea, the hazy white sky begins to darken to a deep, uniform gray. The first drops land in the red dust, each one a dark, spreading stain. A phytosaur, resting its long snout on a riverbank, might have felt the first impacts on its armored hide, an unfamiliar sensation in what should have been the heart of the dry season. The first drops were not a relief. They were a sign that the fundamental clockwork of the planet had broken. What began as a localized shower would have triggered a cascade. As rain falls, it cools the column of air beneath the clouds. This cooling forces more of the surrounding, supersaturated air to condense, creating more rain. This process, known as self-precipitation, would have caused the storm to grow and intensify with explosive speed. A shower would become a downpour would become a deluge. The storm front would have spread across the landscape, not as a passing cloud, but as a permanent planetary phase shift. This was not a storm as we know it. It was not a system that would exhaust itself and move on. The underlying engine was still running. The oceans, heated by the greenhouse effect, were still evaporating water into the atmosphere at a prodigious rate. The sky was being refilled with moisture as quickly as it was being emptied. It was a perfect, self-sustaining loop. Evaporation fed the clouds produced the rain, and the rain fell back to the surface, where the planet's high temperature would ensure the cycle began again, immediately and without pause. The old Pangaean mega-monsoon, the predictable rhythm of wet and dry, had been replaced by a monotonous, unending state of wetness. Across the supercontinent, the familiar patterns of life were being erased. The dry season never returned. The months of baking sun and clear skies were a memory that would fade with the generation that had last seen them. The sound of the world was now the constant drumming of water on rock and earth. For the creatures of the Triassic, the initial moments of the rain may have been unremarkable. But as the hours turned into days, and the days into weeks, a horrifying new reality would have begun to dawn. The rain was not stopping. The sky had broken, and it showed no signs of healing itself. The true flood had begun. The first days of the rain would have become a week. The week would have become a month. The seasons would have failed to turn, and the creatures of the Triassic would have slowly, generation by generation, forgotten that the world had ever been any different. The memory of a hot, dry sun in a clear blue sky would have faded from whatever passed for instinct, becoming a ghost story from a lost and almost mythical past. We call it the Carnian Pluvial episode, an episode, as if it were a brief chapter, but its duration is a span of time that defies our human scale comprehension. The rain fell for 2 million years. Let us try for a moment to grasp that timescale. Our own species, Homo sapiens, emerged in Africa around 300,000 years ago. The entire story of humanity, our journey out of Africa, the Stone Age, the invention of farming, the rise and fall of empires, the Industrial Revolution, our first steps on the moon, all of it fits into a period less than 1/6 the length of this single continuous storm. More than 30,000 generations of a creature with the lifespan of a large reptile would have been born, lived, and died under a perpetually weeping sky. For these animals, a rainless day would have been as alien to their experience as a world without gravity would be to ours. The rain was not weather. It was the fundamental state of the world. For those who live in the monsoon tropics, the sound of a heavy downpour is a familiar, often comforting, rhythm. The roar of water on a roof, the drumming on broad leaves, the gurgle of overflowing drains. Now imagine that sound never, ever stopping. The constant, percussive noise of water striking every surface would have been the new silence. The world would have been loud, a monotonous white noise of falling water that would have masked the footsteps of predators and prey alike. The light would have been different too. The sun would be a hidden memory, a diffuse pearlescent glow behind a permanent veil of iron-gray cloud. The world would have lived in a perpetual twilight, a damp, gloomy world of soft shadows and muted colors. The air, thick with moisture, and the scent of wet earth and rotting vegetation would have been heavy in the lungs. And the vegetation itself would have transformed. The hardy, dry-adapted seed ferns and conifers that dominated the arid Pangean landscape would have been unable to cope. Their roots would have been drowned in the waterlogged soil, their bodies succumbing to fungus and rot. In their place, a different kind of green kingdom would rise. This was a world made for ferns, for mosses, and for the giant relatives of club mosses known as lycophytes. These plants, which reproduce via spores rather than seeds, are perfectly adapted to a life of dampness. Spores could be transported by the endless rivulets of water, and the plants themselves thrived in the low light and saturated ground. Pangaea, the great red desert continent, was slowly turning a deep, wet green. Was this rain truly continuous, everywhere, for the entire 2 million years? This is a question scientists are still working to answer. The term pluvial suggests rain, but the reality was likely more complex. Climate models suggest that the rainfall was probably most intense and relentless in the equatorial regions, particularly around the warm Tethys Sea. Here, the downpour may have been truly ceaseless. In the higher latitudes, further from the equator, the rain might have been more episodic. There could have been brief pauses, a day, a week, where the rain lessened to a drizzle, or even stopped, before the clouds inevitably gathered and the deluge began again. But even in these regions, the world was defined by water. The ground never had a chance to truly dry. It was a spectrum of wetness, from perpetually flooded to merely saturated. The nature of the rain itself would have been violent. The superheated, moisture-laden atmosphere was a colossal energy engine. This would have fueled intense convective storms. We should not imagine a gentle English drizzle, but rather a relentless, tropical-style downpour with raindrops the size of bullets falling from a turbulent sky. The world was being continuously assaulted by its own atmosphere. This was the new reality. A gray, loud, damp, and dimly lit world where the very concept of a dry season had been erased. Life, which had adapted over eons to a world of thirst, now faced the opposite crisis. A world drowning in an endless abundance of water. Once the rain began to fall, it had to go somewhere. The first water to hit the baked red soils of the Pangean desert would have done little more than turn the dust to mud. But as the downpour continued relentlessly, this mud would have been set in motion. Flash floods of red, sediment-laden water would have poured across the landscape, following the paths of least resistance, filling ancient dry riverbeds and carving new ones with a sudden, violent energy. This was the first act of a planetary-scale reshaping. Water, the most patient and powerful of all sculptors, was beginning its work. Over the years and centuries, these ephemeral floods would coalesce into permanent rivers. The arid heart of the supercontinent, for millions of years a place where water vanished into the sand, now became the birthplace of immense, continent-spanning river systems. We must not imagine these as neat, tidy rivers like the Thames or the Seine, confined to a single channel. The Triassic rivers would have been vast, chaotic, and untamed. They would have been braided rivers, a form common in landscapes with huge volumes of water and sediment. Picture a river miles wide, a sprawling network of countless, interlocking channels that constantly shifted, separated by temporary islands of sand and gravel. They would have been gray, choked with the eroded rock and soil of a continent being actively dissolved. The rain was a powerful, erosive force. Every drop that struck the ground dislodged a particle of soil. This effect, multiplied by trillions of drops falling every second for 2 million years, was enough to wear down mountains. The great mountain ranges that had been thrust upwards when Pangaea was formed were now being relentlessly ground down. The world was being flattened, its sharp edges smoothed away. Entire landscapes were stripped of their topsoil, which was then carried away by the ever-growing rivers, a constant flow of the continent's substance towards the sea. All of this eroded material, this sand, silt, and clay, had to be deposited somewhere. As the rivers flowed from high ground to low, they would slow down, lose their energy, and drop their heavy load of sediment. Immense inland basins began to fill, creating vast flat floodplains and wetlands stretching for thousands of square kilometers. Great deltas formed, not just at the coast, but wherever a river entered a large flat basin. This is a process we can still see today in the great river deltas of our own world, like those of the Mekong or the Amazon, where mighty rivers lay down the foundations of new land. On Pangaea, this process was happening on an unprecedented scale, burying the old desert world under a thick blanket of new, waterborne rock. Where the water could not easily drain, it began to pool, filling vast geological depressions in the supercontinent's surface. This was the birth of the great Pangean lakes. Some of these may have grown to the size of inland seas, vast bodies of fresh water, where before there had been only sun-baked salt flats. Geologists find the evidence for these lost lakes today in the form of fine-grained shales and mudstones, rock types that can only form at the bottom of still, quiet water. The exact nature of these lakes is still a mystery. Were they permanent features that lasted for millennia, developing their own unique ecosystems? Or were they more temporary, existing for centuries before they were filled with sediment, or the river systems found a new path, leaving behind a vast mudflat? It is likely that both were true, with Pangaea becoming a mosaic of permanent lakes and ephemeral shifting wetlands. This is how the world turned from red to green and gray. The green was the explosion of ferns and mosses we spoke of. The gray was the new dominance of water and mud. It was the color of the sky, reflected in the surface of 1 million square kilometers of lake water. It was the color of the sediment-choked rivers, a slurry of rock and water flowing ever onwards. And it was the color of the vast, sodden mudflats that now defined much of the landscape. The old stark beauty of the red desert was gone, replaced by a softer, wetter, more monotonous world. The fundamental geography of Pangaea was being rewritten. The stage was being flooded, and the creatures that lived upon it would now face their own crisis. Into this newly sculpted world of rivers, lakes, and mud, the terrestrial life of the Triassic was now cast adrift. The very ground beneath their feet, the one constant of their existence, had betrayed them. The rules of survival, honed over millions of years in a hot, arid world, were now obsolete. The constant rain and the transformed landscape created a powerful environmental filter, a global test that would spare some, but doom many others. For the great ruling reptiles, the crocodile-line archosaurs that had dominated Pangaea, this new world was a bewildering and hostile place. Consider the ettosaurs, the great armored herbivores. Their heavy bodies and short, stout legs were built for firm, dry ground. Now they found themselves navigating a world of deep, clinging mud that would exhaust their energy with every step. Their armor, once a defense against predators, now became a dead weight, threatening to bog them down in the mire. More critically, their food was gone. The hardy, arid-adapted plants they were specialized to eat had rotted away, replaced by a monotonous carpet of ferns and mosses, which may have been less nutritious or even indigestible to them. Their predators, the mighty rauisuchians, faced a similar crisis. As the herbivore populations struggled and declined, so too did the food source for the apex carnivores. Hunting in the newly dense, fern-choked lowlands would have been difficult, visibility obscured, the ground treacherous. The entire food web, from the plants at its base to the predators at its peak, was collapsing under the strain of the endless water. We have poignant, direct evidence of this struggle, frozen in stone. Paleontologists have discovered fossil trackways, or trace fossils, from this period. These are not the bones of the animals, but the preserved footprints they left behind as they moved across the wet landscape. They tell a story that bones cannot. They show the footprints of large archosaurs slogging through deep, soft mud, the substrate squishing up around their feet. They are a snapshot of a moment of exertion, a direct window into the daily arduous reality of life in a drowning world. The precise cause of the extinctions that followed is still a matter of debate among scientists. Was it simply starvation, a slow decline as the old food web withered away? Or did the damp, warm conditions foster new deadly pressures? It is very likely that diseases from fungal infections to parasites would have flourished in this global swamp, spreading rapidly through populations of animals that had no evolved resistance to them. The crisis for life was likely a death by 1,000 cuts, loss of habitat, loss of food, the difficulty of movement, and the constant pressure of disease. But as with any great crisis, there were those who were not just surviving, but thriving. The new world filtered for a different kind of creature. The great salamander-like amphibians, such as the car-sized Metaposaurus, had always been tied to the water. For them, this was not a crisis, but an opportunity. Their world of ponds and swamps was now expanding to cover a continent. They were perfectly at home in the shallows of the new Pangaean lakes. The phytosaurs, those crocodile mimics that already ruled the rivers, also found their dominion expanding with every new waterway that was carved into the land. And what of the dinosaurs? For millions of years, they had been minor players, small bipedal creatures living in the shadows of their larger archosaur cousins. Now, some of their key features were proving to be unexpected advantages. Their upright, two-legged stance and efficient, hinge-like ankles may have made them more nimble and better able to navigate the treacherous, muddy ground than the heavier, four-legged rauisuchians. Their smaller bodies required less food, and many were likely generalists, able to scrape by on insects, small vertebrates, or whatever they could find. They were not yet thriving, but they were enduring. They were passing through the environmental filter that was snaring their larger, more specialized competitors. A great reordering was beginning to take place on land. The old guard was failing. their adaptations now liabilities. The world was being cleared, not by fire and brimstone, but by the slow, relentless pressure of mud and water. The crisis on the land did not happen in isolation. Every river swollen with mud and the dissolved remains of a dissolving continent had a destination: the sea. The endless rain was a conveyor belt, transporting the catastrophe from the terrestrial realm into the marine. For the vibrant, recovering ecosystems of the Tethys Sea and the Panthalassic Ocean, an assault was coming, not from a predator, but from the land itself. Imagine standing at the coast of Pangaea. The line between land and sea would have become blurred. Immense, muddy plumes would extend for hundreds of kilometers from the mouths of the new rivers, turning the clear tropical waters into a murky brown soup. This was not merely a discoloration. It was a fundamental alteration of the marine environment, and it brought with it a trio of devastating pressures. The first was the sheer volume of fresh water. The rain falling on the continent was fresh, and it poured into the salt water of the oceans, drastically lowering the salinity near the coasts. For marine organisms that are finely tuned to a specific salt concentration, this was a chemical poison. The most immediate victims would have been the new, fragile reefs built by the scleractinian corals. These tiny animals, the architects of a new marine world, could not survive the freshwater intrusion. The very water that surrounded them had become toxic. The second pressure was the sediment. The mud and silt carried by the rivers did not simply disappear. As the river water slowed upon meeting the ocean, this sediment fell out of suspension, blanketing the seafloor in a thick layer of fine mud. For the coral reefs, this was a death sentence. It smothered them, burying the coral polyps alive. It also blocked the sunlight, starving the symbiotic algae that live within the corals and provide them with most of their food. The new stony cities of the Triassic seas were being buried, their light extinguished. This is a tragedy that echoes in our own time, as modern coral reefs, so vital to the health of our planet, face similar threats from pollution and sediment runoff. The third and most widespread pressure was more insidious. The soils washed from the land were rich in nutrients like nitrogen and phosphorus. In the ocean, these nutrients acted as a super fertilizer, triggering colossal blooms of algae and bacteria at the surface. For a time, the seas would have been choked with a thick, green scum, but when this massive amount of organic matter died, it sank into the deep. There, its decomposition by other bacteria consumed vast quantities of dissolved oxygen from the water, creating immense dead zones, a condition known as ocean anoxia. The geological signature of this crisis is stark. In rock formations from this period around the world, geologists find layers known as black shales. These rocks are dark, almost black, from the sheer amount of undecomposed organic matter they contain, and they are finely layered, or laminated. This lamination tells a story of a seafloor devoid of life. In a healthy ocean, the bottom is constantly churned by burrowing worms, clams, and other creatures. In an anoxic ocean, these animals cannot survive. When they die, the fine layers of sediment and dead plankton settle in a perfect undisturbed sequence, like pages in a book. These black shales are the tombstone of a suffocated ocean. The crisis cascaded through the marine food web. The plancodonts, the shell-crushing reptiles of the shallows, would have found their food source buried under mud. The amphibious nothosaurs would have found the coastal waters murky and lifeless. Even the great ichthyosaurs, masters of the open ocean, would have been profoundly affected. While the surface waters might have remained oxygenated, the anoxia spreading in the deep would have destroyed the foundations of their food supply. The ocean, which had seemed a boundless refuge, was now facing its own silent, suffocating catastrophe. It was a perfect storm of deadly factors, and scientists still debate which blow was the most severe. Was it the fresh water, the mud, or the anoxia that ultimately destroyed the coastal ecosystems? The most likely answer is that it was the relentless combination of all three. The world was now facing a crisis on two fronts. Life on land was drowning, and life in the sea was suffocating. The combined pressure of a drowning land and a suffocating sea was more than the fragile, recovering biosphere could bear. This was a true mass extinction event. While it lacks the fame of the asteroid impact that would end the age of dinosaurs, the Carnian pluvial episode was a profound biological crisis, a great filter that dramatically reshaped the tree of life. It was a quiet, drawn-out apocalypse, a war of attrition waged by the sky against the inhabitants of the earth. When the waters finally receded, the world was a much emptier place. Let us call the roll of the lost and pay our respects to the worlds that vanished. In the seas, the devastation was profound, particularly in the shallow coastal waters. The young, experimental reefs, built by the first scleractinian corals, were all but annihilated. The fossil record shows what paleontologists call a reef gap that lasted for millions of years after this event. The evolutionary experiment of building stony cities beneath the waves, which had just begun, was almost extinguished entirely. The world's oceans became, for a time, a world without the architectural complexity that reefs provide. With the reefs and the shallow seafloor ecosystems gone, the animals that depended on them soon followed. The placodonts, those strange armored reptiles with crushing teeth, had made their living eating shellfish in the lagoons. With their habitat poisoned and their food source buried in mud, their unique evolutionary path came to a dead end. They vanished completely from the fossil record. The nothosaurs, the amphibious, seal-like hunters of the coasts, also disappeared. Their strategy of bridging the worlds of land and sea became untenable when both realms were in a state of collapse. One of the most significant losses in the marine realm was a group of creatures called the conodonts. For 300 million years, these small eel-like vertebrates had been one of the most abundant and widespread groups on the planet. They are known almost entirely from their tiny, intricate, tooth-like fossils, which are so common and evolved so quickly that geologists use them as a primary tool for dating marine rocks. The conodonts had survived the Great Dying, the most severe extinction of all time, but the crisis of the Carnian pluvial episode was the final blow. After a reign that had lasted longer than the dinosaurs, their long story finally came to an end. Their sudden disappearance is one of the key markers that tells geologists they have crossed a major boundary in the history of time. On land, the losses were just as severe. The old guard, the rulers of the dry Triassic, were swept away. The great atosaurs, the walking fortresses, vanished from the record. Their heavy, armored bodies were ill-suited to the swampy world. The mighty Rauisuchians, the apex predators of their day, also disappear. The top of the food pyramid had collapsed. This left a profound power vacuum in terrestrial ecosystems, an opening for a new dynasty of predators to eventually fill. It was not just the ruling reptiles that suffered. The dicynodonts, a successful group of tusked, herbivorous mammal relatives, were also decimated. These creatures had been a major component of land ecosystems for tens of millions of years, but the destruction of the arid adapted flora sealed their fate. Only a few lineages would cling on for a little while longer before fading away. Even many of the giant amphibians, like Metaposaurus, which thrived during the peak of the rains, seem to have disappeared when the climate eventually shifted back to drier conditions. They were beneficiaries of the crisis, but could not survive the recovery. The fossil record is clear that a great dying occurred, but the mystery lies in its tempo. Was this a single, sharp blow? A pulse of extinction lasting a few thousand years in the middle of the long rain? Or was it a slow, grinding decline? A war of attrition where species winked out one by one over the full 2 million years. The resolution of our geological clock is often not fine enough to distinguish between these scenarios. It is like reading a book where most of the pages are missing. We see the beginning and the end of the chapter, but the precise sequence of events within it is lost to the silence of deep time. What is certain is that a world had ended. Entire branches of the tree of life, each a unique an unrepeatable experiment in how to exist, were pruned away forever. The planet had been reset. The board was being cleared, leaving a quiet, empty stage for the survivors to step out upon. In the face of such a complete and prolonged global crisis, it is a genuine wonder that life was not extinguished entirely. A drowning land and a suffocating sea would seem to offer no escape, and yet, life is resilient. It clings to existence in the most improbable of places. Even in a world drenched by a 2-million-year storm, there were sanctuaries. There were islands of survival in a sea of chaos. Biologists call these places refugia. A refugium is a location where a population of organisms can survive through a period of otherwise unfavorable conditions. Even in a global event, like the Carnian pluvial episode, the effects were unlikely to have been perfectly uniform across the entire face of Pangaea. Local geography and geology would have created pockets, havens, where the worst of the deluge was held at bay. The search for these ancient sanctuaries is one of the great detective stories in paleontology. Some of the most likely refugia would have been in the highlands. While the great basins and lowlands were transformed into endless swamps and lakes, the mountain ranges and high plateaus would have been better drained. Here, patches of solid, or at least less sodden, ground may have persisted. For terrestrial animals, these uplands would have been literal islands, isolated by the impassable wetlands that now dominated the world below. Life would have been concentrated in these elevated havens, creating crowded, competitive ecosystems where the survivors of the old world were forced into close quarters. Other sanctuaries may have been found in the rain shadows of the great Pangaean mountain ranges. Just as modern mountains force moisture out of the air on one side to create a dry region on the other, so too would have the mountains of the Triassic. While the rest of the world was being battered by torrential rain, these sheltered valleys may have experienced a climate that was merely damp, a profound and life-saving difference. Perhaps the most crucial sanctuaries, however, were not on the surface, but beneath it. The high levels of carbon dioxide that fueled the crisis also had a curious side effect. They made the rain acidic. This was not a corrosive, flesh-stripping acid, but a mild carbonic acid, the same thing that gives carbonated drinks their fizz. Over thousands of years, as this acidic rain fell upon regions of Pangaea that were underlain by limestone, it began to dissolve the rock. Water seeped into cracks, widening them into passages, carving out great chambers, and creating vast, intricate networks of caves. This is the very same process that has created the magnificent karst landscapes we see in our own world. From the great cenotes of Mexico to the spectacular caves and limestone towers of Southeast Asia. We can imagine that during the Great Rain, Pangaea's limestone regions were being hollowed out, creating the most perfect of all possible shelters. These caves would have offered a refuge from the relentless downpour, stable temperatures, and protection from the mudslides and flash floods that constantly scoured the surface. Here, in the deep, quiet, dark, small animals could have survived. Early mammals and their relatives, lizard-like reptiles, and the small, nimble dinosaurs could have found a haven, emerging to forage in a world where their larger competitors could not survive. Identifying the exact locations of these ancient refugia is incredibly difficult. Scientists hunt for clues in the rock, searching for geological formations that speak of a slightly drier, more stable environment amidst the widespread evidence of flooding. But it is like searching for a single street on a map of a long-vanished city. We know these places must have existed because the story of life did not end. The survival of so many lineages is the ultimate proof that these islands of hope were real. These refugia were more than just waiting rooms for the apocalypse to end. They were crucibles of evolution. In these isolated, crowded pockets, the pressures of natural selection would have been immense. The survivors were thrown together, forced to compete for limited resources in a radically new environment. It would have favored the adaptable, the resourceful, and often the small. It was in these hidden valleys and deep caves that the future was being forged. The creatures that would inherit the next world were not the great rulers of the old one, but the humble, tenacious survivors who had found a way to weather the storm. No engine, not even one of planetary scale, can run forever. The 2-million-year reign was a powerful, self-sustaining cycle, but the very forces that unleashed it also contained the mechanism for its demise. The planet, in its own slow geological way, began to heal itself. The recovery was not driven by life, but by the patient, silent chemistry of rock and water. The accelerator for the crisis had been the immense injection of volcanic carbon dioxide. The brake, it turned out, was the rain itself. The same high levels of CO2 that were trapping heat in the atmosphere were also being dissolved in the raindrops, forming a mild carbonic acid. As this acid rain fell relentlessly for 2 million years, it reacted with the rocks of the landscape. Specifically, it reacted with silicate minerals, the most common type of rock on the Earth's surface. This chemical process, known as silicate weathering, breaks down the rock and, in doing so, pulls carbon dioxide directly out of the atmosphere. This is the Earth's primary long-term thermostat. The dissolved minerals from this reaction, now containing the captured carbon, were carried by the new, mighty rivers into the ocean. There, marine organisms, like plankton, would use these compounds to build their shells of calcium carbonate. When these organisms died, they would sink to the seafloor, taking the carbon with them. Over millennia, this would be buried and turned into limestone, locking the excess atmospheric carbon away in the deep geological archive. This process is always happening, but it is incredibly slow. The Carnian pluvial episode put this planetary thermostat into overdrive. The constant rain, the warm temperatures, and the vast amounts of freshly eroded rock exposed by mudslides all conspired to dramatically accelerate the rate of weathering. The Earth was scrubbing its own atmosphere. At the same time, deep in the crust, the volcanic activity of the Rangelia province would have begun to wane. The great fissures would have cooled and sealed. The rate of new CO2 being pumped into the sky slowed to a trickle, while the rate of removal by weathering was at an all-time high. The balance finally tipped. For the first time in 2 million years, more carbon dioxide was being removed from the atmosphere than was being added. Slowly, imperceptibly, the concentration began to fall. As the CO2 blanket thinned, the greenhouse effect weakened and the planet began to cool. As the atmosphere cooled, its capacity to hold moisture decreased. The great engine of evaporation and precipitation began to lose its power. The storm began to falter. The end would not have been a single dramatic moment. It would have been a slow, hesitant return to normalcy. In one region, the rains might have stopped for a week, letting the ground steam under a hazy sun before the deluge returned. The next year, that dry spell might have lasted a month. The forgotten rhythm of the seasons was trying to re-establish itself. The monotonous roar of the rain was being punctuated by moments of profound silence. The geological evidence for this shift is as clear as its beginning. On top of the dark gray and black mudstones that characterize the wet period, geologists find the return of a rock type known as red beds. These are sandstones and shales with a distinctive reddish color, which comes from iron minerals that have been oxidized or rusted. This rusting can only happen in an environment with free oxygen and alternating wet and dry seasons. The return of the red beds is the planet's signature, a clear and unambiguous signal that the great rain was over. The arid world of Pangaea was returning. The mystery is whether this return was a gentle, gradual process or a chaotic one. Did the climate swing wildly for a few thousand years, with intense droughts followed by punishing floods, before finally settling down? The end of the crisis may have been a turbulent time in its own right, a final series of convulsions before a new kind of stability was found. But eventually, the quiet came. Imagine the first generation of creatures to experience a truly prolonged dry season, the first to feel the warmth of direct sunlight on their skin, the first to hear the sound of the wind without the percussive accompaniment of the rain. For the inhabitants of the refugia, Peering out from their caves and highland valleys, it would have been a new and almost alien world. The stage, which had been flooded for an eternity, was finally drying out. It was a scarred, transformed, and strangely empty world. But it was a world of profound and boundless opportunity for those who had endured. The first silence after the rain would have been profound, but it would not have lasted long. A new sound would have slowly filled the air, the rustle of the wind through leaves. The world, scoured clean and left as a blank canvas of gray mud, was ready to be painted green once more. The botanical kingdom was the first to reclaim the empty continent, and in doing so, it laid the foundation for the entire world to come. In the immediate aftermath, the world would have been dominated by the survivors of the flood, the ferns, mosses, and lycophytes. These spore-bearing plants, which had thrived in the endless dampness, would have formed a low green carpet over the saturated ground. But they were children of the water, forever tied to a life of moisture. As the great Pangean deserts began to re-establish themselves, as the forgotten rhythm of the dry season returned, these plants would have retreated, clinging to the damp riverbanks and the shores of the Great Lakes. Their temporary reign was over, and the vast drying plains of the continent were left open, an opportunity of a planetary scale. From the refugia, from the sheltered highland valleys and dry rain shadows, came the pioneers of this new world. They were a group of plants that had existed long before the crisis, but had never been truly dominant. They were the conifers. The Great Extinction event had swept away their main competitors, particularly the once mighty dicroidium seed ferns. Now, in a world wiped clean, the conifers' unique set of adaptations made them perfectly suited to inherit the earth. Unlike ferns, conifers reproduce with seeds. A seed is a marvel of evolutionary engineering, a tiny self-contained life support system containing an embryo and a packed lunch of nutrients, all wrapped in a tough, protective coat. It can lie dormant for years, waiting for the precise conditions of moisture and warmth to begin to grow. This was an enormous advantage in the new, highly seasonal world. Where a spore had to land on damp ground to survive, a seed could wait for the rains to come. Their bodies, too, were built for this new world. Their leaves had evolved into narrow needles, or tough scales, covered in a waxy coating that was remarkably efficient at preventing water loss during the long, dry seasons. Their strong, woody trunks, reinforced with lignin, allowed them to grow tall, reaching for the newly revealed sun and creating vast shaded canopies. Over the centuries and millennia that followed the rain, a great green wave of these new conifers would have spread out from the refugia, colonizing the barren plains. Imagine the slow-motion spectacle. The first hardy saplings taking root in the mud, and then, generation by generation, the expansion of the first true forests of the new era. The uniform green carpet of ferns was replaced by the textured, deep green spires of the ancestors of modern pines, cypresses, and araucarias. These new forests were not silent. They were filled with the hum of insects, and the trees evolved a new defense. They produced a sticky, aromatic substance called resin. This resin would seal wounds in their bark, protecting them from infection, and crucially, it would trap and entomb any insects that tried to bore into the wood. This ancient resin, when fossilized, becomes amber, and it is thanks to this Triassic innovation that we have a perfect microscopic view of the small creatures that inhabited these forests, trapped like flies in golden time capsules. Why did the conifers triumph so completely? Was it because their adaptations were inherently superior in the post-deluge world? Or was it simply a matter of opportunity? Had the Great Extinction merely cleared the board of their competitors, leaving them to fill an empty house? This remains a quiet debate in paleobotany. The answer is likely a combination of both. They were the right plant, in the right place, at the right time. This botanical revolution was the single most important event of the recovery. These new forests stabilized the soil, preventing the runaway erosion of the rain-scoured world. They created a vast new habitat, a complex three-dimensional world of trunks, canopies, and shaded forest floors. And they created a massive new source of food. The descendants of these pioneering trees still stand on our planet today, in the great boreal forests of the north and in the high mountains of places like Europe, the Americas, and even Southeast Asia, living links to this moment of planetary rebirth. The world was no longer empty, it was forested. And into these new quiet woods, the animal survivors were about to take their first tentative steps. Into the silent, new-growth forests of conifer and fern, the animal survivors began to emerge from their sanctuaries. They stepped out into a world that was both familiar and profoundly different. The air was breathable, the ground was solid, but the cast of characters had been irrevocably changed. The Great Extinction Event had created a power vacuum. The ecological niches of large herbivore and apex predator, long occupied by the mighty crocodile-line archosaurs, were now empty. The thrones of the world were vacant, and for the first time in millions of years, there was an opportunity for a new dynasty to rise. This phenomenon is known as competitive release. Imagine a small, humble plant growing in the shadow of a giant tree. It receives little light, few nutrients, and struggles to survive. Then a storm fells the great tree. Suddenly, the small plant is bathed in sunlight. Its roots have room to grow, and it can flourish, expanding to fill the newly available space. In the aftermath of the great rain, the dinosaurs were this small plant, and all the giant trees had fallen. For tens of millions of years before the crisis, the dinosaurs had been a minor group, living in the margins. They were small, bipedal, and fast, but they were consistently outcompeted by their larger, more diverse archosaur relatives. But they had survived the filter. Their key adaptations, honed as a marginal group, now became the very tools they needed to inherit the world. Their upright posture and efficient, hinge-like ankles, which we have spoken of, allowed them to move with speed and stamina across the vast recovering plains. But they held another secret advantage, hidden deep within their bodies. Dinosaurs were developing a respiratory system unlike any other reptile. It was a precursor to the system we see in modern birds, a one-way flow of air supported by a series of air sacs throughout the body. These air sacs even extended into their bones, making them hollow and light, yet incredibly strong. This hyper-efficient breathing apparatus would have been a crucial advantage in the low oxygen atmosphere of the Triassic. It would have supported a higher metabolism, giving them more energy and endurance than their surviving competitors. They were, in a very real sense, built for this new, post-crisis world. And so their great expansion began. From the few surviving lineages, a spectacular evolutionary radiation was sparked. This was the true dawn of the age of dinosaurs. The first of the great dinosaur groups began to diversify and specialize, stepping into the roles left vacant by the extinctions. We see the rise of the first true theropods, the lineage of bipedal carnivores, that would eventually lead to giants like Tyrannosaurus rex. In the late Triassic, they were creatures like Colophysis, slender, fast hunters, perhaps no larger than a wolf, that would have darted through the new conifer forests, hunting small reptiles and the first furry mammals. At the same time, we see the beginnings of the great herbivorous lineages. The sauropodomorphs appear, the ancestors of the colossal long-necked sauropods of the Jurassic. But they did not start as giants. They were creatures like Plateosaurus, which could walk on 2 legs or 4 and had a moderately long neck, perfect for browsing on the tough needles of the newly dominant conifers, reaching a food source that smaller herbivores could not. They were the first high browsers, and they were beginning to grow, a sign of the immense size their descendants would one day achieve. The pace of this takeover is a fascinating mystery. Was it an explosive, sudden radiation, with new species appearing in a geological flash as soon as the world dried out? Or was it a more gradual ascent, a slow and steady process of diversification over millions of years as they slowly pushed out the few remaining competitors? The fossil record is patchy, offering tantalizing but incomplete glimpses of this pivotal moment. What is clear is that the dinosaurs were seizing the day. Their reign would eventually extend across all of Pangaea, from the forested South Pole to the northern coasts. Their fossils would be laid down on every future continent, a testament to a dynasty forged in a time of crisis. Their descendants would eventually walk upon the very land that, after 200 million more years of continental drift, would become the mountains and lowlands of Asia, Europe, the Americas, and Africa. The Carnian pluvial episode had not been the end of the world. It had been a crucible. It had tested all life, broken the old rulers, and cleared the stage. And now, onto that stage, the dinosaurs were stepping, not with a sudden roar, but with the quiet, inexorable confidence of a lineage whose time had finally come. While the dinosaurs were taking their first steps towards empire on land, a parallel revolution, a quiet and patient rebuilding, was beginning beneath the waves. The oceans, particularly the coastal seas, had been left scoured and depleted by the crisis. The relentless runoff of fresh water and mud had silenced the reef-building corals, creating a profound emptiness in the marine world. For millions of years, what is known as a reef gap persists in the fossil record, a testament to a world where the great architectural work of life had ceased. But in the deep, quiet corners of the ocean, in forgotten refugia, the survivors had held on. As the rain stopped and the rivers of Pangaea began to run clear, the seas slowly healed. The immense plumes of sediment dissipated, and the water, once a murky brown, returned to a brilliant blue. Salinity levels stabilized. Sunlight, for so long blocked by mud and algal blooms, could once again penetrate deep into the water column. The conditions for life and for building had returned. And the master builders of our modern world, the scleractinian corals, began their patient work anew. Imagine a single microscopic coral larva drifting on the ocean currents. It is a survivor, the descendant of a lineage that weathered the storm. It settles on a clean piece of rock on the seabed, the tomb of an older forgotten reef. There it transforms, building a tiny limestone cup around its soft body. This is the first brick laid in a new global city. The polyp then begins to clone itself, budding off identical copies, and the colony expands, millimeter by millimeter. It is a process of immense slowness, a construction project that operates on a geological timescale. The extinction event, while devastating, had also cleared the field of competitors. Other reef-building organisms, like certain types of sponges and algae, had also been hit hard. The scleractinian corals, for reasons that are still a mystery to us, were simply the best adapted to capitalize on the recovery. Why them? What gave these tiny animals the evolutionary edge that would allow them to become the planet's dominant reef builders for the next 230 million years? A reign that continues to this day? Perhaps the new ocean chemistry, enriched with the dissolved minerals from 2 million years of continental weathering, was perfectly suited to their biology. Perhaps their symbiosis with photosynthetic algae gave them a crucial metabolic advantage. Whatever the reason, their time had come. As these new reefs grew, they became more than just structures. They became engines of evolution. The simple, patchy reefs of the early Triassic gave way to far more complex three-dimensional structures with countless nooks, crannies, caves, and overhangs. This new architecture created thousands of new ecological niches, and life rushed in to fill them. A co-evolutionary dance began between the reef and its inhabitants. New species of fish evolved, with flattened bodies to navigate narrow crevices or powerful beaks to crunch coral. New types of crabs, shrimps, and mollusks appeared, each specialized for a particular life within the reef's complex society. This was the birth of the modern reef ecosystem, the intricate, bustling, and dazzlingly diverse coral reefs that grace our planet's tropical waters today are the direct, unbroken legacy of this Triassic recovery. The very foundations of the Great Barrier Reef, or the vibrant reefs that fringe the islands and coasts of the Caribbean and Southeast Asia, were laid by these tenacious survivors in the aftermath of the Great Rain. The patient work of those first coral polyps, building their limestone homes in a quiet and empty sea, was the beginning of the world we now know. A parallel story was unfolding. On the drying plains of Pangaea, the dinosaurs, a dynasty of giants, were on the rise. In the clearing seas, the corals, a dynasty of tiny architects, were beginning a construction project that would last for hundreds of millions of years. The two great pillars of the Mesozoic world were being set in place. The age of reptiles on land and the age of modern reefs in the sea were both born from the fire and water of the Carnian pluvial episode. Let us now take a step back. To a vantage point high above the timeline of our story, we have witnessed a world torn down and rebuilt. We have seen dynasties fall and new ones rise from the mud. The Carnian pluvial episode was more than just a long storm. It was a planetary reset button. In the grand, sprawling story of life on Earth, there are moments of profound crisis that act as narrative pivots, clearing the slate for a completely new chapter. This was one of them. This pattern is sometimes called creative destruction. Like a forest fire that, while devastating, clears out the old, tangled undergrowth and enriches the soil, allowing a flush of new, diverse life to spring forth. A mass extinction can reset the evolutionary clock. It ends the dominance of groups that have become too specialized, too entrenched, and opens up the field for new experiments, new body plans, and new ways of life to be tested. The 2-million-year reign was the fire, or rather the flood, that cleared the world of the Triassic and paved the way for the world of the Jurassic. Before this event, the world was a strange mix of old and new. It was a world of survivors from the Great Dying, like the mammal relative Dicynodonts, clinging to a legacy that stretched back into the previous era. It was dominated by the diverse and powerful crocodile line archosaurs, a grand experiment that, in a different world, might have continued its reign for another 100 million years. And it was a world where dinosaurs were a minor, almost trivial part of the ecosystem. After the event, the picture is completely different. The old guard is gone. The world belongs to the dinosaurs. The conifer forests they inhabit are new. The modern-style reefs in the oceans are new. It is the true beginning of the Mesozoic era, as we popularly imagine it, the age of dinosaurs. The CPE was the crucible in which this world was forged, and it was not only the dinosaurs who benefited from this reset. Hiding in the undergrowth of the new conifer forests, another group of survivors was quietly carving out a new existence. The first true mammals were appearing, descended from the cynodonts, a group of mammal relatives that had also weathered the storm. These creatures were small, furry, and likely nocturnal. They were shrew-like animals, surviving in a world of giants by being secretive, by moving through the night, and by having a high metabolism that allowed them to be active in the cool of the dark. Their time of dominance was still more than 150 million years in the future, but their survival and diversification in the aftermath of the CPE was the critical step that ensured their story, and therefore our own, would continue. In the skies, too, a new experiment was taking flight. The first pterosaurs, those remarkable winged reptiles, were diversifying, taking advantage of the new forest canopies and the abundance of insects. The air was being conquered by vertebrates for the very first time. This raises a profound question about the nature of evolution. Was the rise of these new groups a story of a long fuse or a short fuse? In the long fuse model, groups like the dinosaurs already possessed all their key adaptations, their efficient breathing, their upright stance, long before the crisis, and were simply waiting in the wings for millions of years for the opportunity to shine. The extinction was merely the opening of the curtain. In the short fuse model, the chaos of the post-extinction world itself was the driver of innovation, actively forcing these groups to rapidly evolve the new traits they needed to survive and thrive. The truth, as is often the case, likely lies somewhere in between. It was a perfect meeting of preparation and opportunity. The story of the Great Rain is therefore a powerful lesson in contingency. It reminds us that the world we know is not the result of an inevitable, predictable progression. It is the product of chance events, of geology, of cosmic cycles. If the Rangelia volcanoes had been less active, or if the geography of Pangaea had been slightly different, the reign of the dinosaurs might never have begun. Our own mammalian ancestors might have faded into obscurity. The story of life is a fragile, unpredictable narrative, shaped as much by catastrophe as by gradual adaptation. It is a cycle of renewal, of worlds ending, so that new ones can begin, a rhythm that echoes through the quiet of deep time. The story we have told so far is a single coherent narrative of fire, water, and life. It is the best story that our current scientific understanding can weave from the available clues. But it is important, in the quiet of this moment, to remember that this story is pieced together from a scattered and ancient text. The history of our planet is a puzzle with most of its pieces missing, and the work of science is to assemble what we can, to see the image that emerges, and to humbly acknowledge the gaps and the uncertainties that remain. The precise cause and mechanism of the Carnian pluvial episode is one such area of vibrant scientific debate. The primary suspect, as we have discussed, is the colossal volcanic eruption of the Rangelia Large Igneous Province. The evidence is compelling. The timing of the lava flows, dated using the slow decay of radioactive elements in the rock, aligns almost perfectly with the beginning of the climate chaos. The sheer volume of the eruption provides a clear source for the greenhouse gases needed to warm the planet. The chain of events, volcanism, warming, humidity, and then rain, is a logical and physically plausible sequence. This is the mainstream consensus view, the backbone of our story. And yet intriguing questions remain. The Earth has seen many large igneous provinces in its history. Some were even larger than Rangelia. The Siberian traps, which caused the Great Dying, were far more vast. The Deccan traps in India, which coincided with the extinction of the dinosaurs, were also immense. Yet neither of those events are associated with a prolonged pluvial or rainy phase. They caused mass extinctions through warming and other means, but they did not cause it to rain for 2 million years. So, the great mystery is, why was Rangelia different? One hypothesis lies in geography. Location is everything. The Rangelia eruptions occurred on the western coast of Pangaea, perfectly positioned next to the warm waters of the Tethys Sea and the immense Panthalassic Ocean. This prime coastal location may have been the key factor that allowed for a massive and continuous injection of water vapor into the atmosphere, a feedback loop that an eruption in a dry continental interior might not have been able to create. Another possibility lies in the specific geology of the crust that Rangelia erupted through. As we touched upon, this region was rich in ancient deposits of coal and limestone. The baked carbon hypothesis suggests that the unique feature of this event was not just the gas from the magma, but the colossal secondary release of carbon from these cooked sediments. Perhaps Rangelia simply had a much greater carbon footprint for its size than other LIPs, providing the extraordinary push needed to break the climate system in this specific way. But science thrives on testing alternative ideas. What if there was another factor at play? High in the wilds of modern-day Quebec, Canada, lies a stunning, ring-shaped lake. It is the Manicouagan Reservoir, and it fills one of the largest and best-preserved impact craters on Earth. An asteroid or comet, perhaps 5 kilometers in diameter, struck the planet here and left a scar 100 kilometers wide. The date of this impact is estimated to be around 214 million years ago. This date is tantalizingly close to the Carnian pluvial episode. Could this impact have been the true trigger, or at least a contributing factor? Some scientists have argued that the timing is too close to be a coincidence. Perhaps the immense dust and vapor thrown into the atmosphere by the impact provided the initial shock that caused the superhumid atmosphere to finally unload its moisture. Others have wondered if the seismic shock of such a colossal impact could have somehow intensified the already active volcanism on the other side of the continent. For now, this remains a minority view. The dates do not line up perfectly, and most evidence still points to the volcanism as the primary long-term driver. But the Great Crater remains, a silent and enigmatic reminder of the violent events of the Triassic, a question mark embedded in the planet's crust. This is how the scientific process works. It is a slow, patient accumulation of evidence, a weighing of possibilities. Geologists, like detectives at a scene that has aged for 230 million years, use every tool at their disposal to reconstruct the events. The story may change as new clues are uncovered. But for now, the picture that emerges is one of a planet pushed past its limit by its own inner fire. A story written not by a single dramatic blow from space, but by the deep, slow, and inexorable forces of the Earth itself. The story of the 2-million-year reign, with all its mysteries and debates, is not a fable. It is a history, and like all histories, it is written down. But its library is not made of paper, and its language is not one of words. The entire story is written in the rocks of our planet, in a slow and patient script of stone, sediment, and chemistry. To understand this event is to learn how to read the Earth's own autobiography. The fundamental principle is called stratigraphy. As sediments, like sand, mud, and silt, are deposited over time, they form layers, with the oldest at the bottom and the youngest at the top. A cliff face, or a road cutting that exposes these layers, is like a book opened to a specific chapter. Each layer is a page, preserving a snapshot of the environment at the moment it was formed. Let us imagine we are geologists, standing before a cliff in the Italian Alps or the mountains of southern China, places that hold some of the most complete records of this time. We would see a story told in color and texture. At the bottom, we would find thick layers of reddish-brown sandstone and mudstone. These are the red beds, their color coming from iron minerals rusted by exposure to the air. They speak of a world of distinct wet and dry seasons, a hot, arid landscape. This is the chapter of Pangaea before the rains. Then, as we look higher up the cliff, the change is abrupt. The red rocks vanish, and they are replaced by a thick sequence of dark gray and black shales, siltstones, and sometimes seams of coal. The color tells us the environment has fundamentally changed. The dark gray color comes from mud laid down in deep, stagnant water. The black color comes from an abundance of organic carbon, the remains of countless plants and plankton that were buried in an oxygen-poor environment where they could not fully decay. The coal, of course, is the compressed remnant of immense waterlogged swamps. This dark, somber band of rock, found on nearly every continent, is the chapter of the Carnian pluvial episode itself. Then, just as abruptly as it appeared, the dark band ends. And above it, the red beds return. The reddish-brown sun-baked sandstones reappear, signaling the end of the swamps and the return of the arid, seasonal world. The entire event is thus bracketed in stone, a dark, wet memory sandwiched between two dry, red ages. Within these layers, we find other, more subtle clues. We find the fossilized pollen and spores that tell us the story of the changing plant life, the sudden disappearance of the dry-adapted conifers, and the explosion of the water-loving ferns. We find the fossil soils that show a shift from dry mineral-rich soils to the waterlogged, peaty soils of a swamp. But perhaps the most powerful clue is invisible to the naked eye. It is a chemical fingerprint. Carbon in our atmosphere comes in two main stable forms, or isotopes. A common, lighter version, carbon-12, and a rarer, slightly heavier version, carbon-13. Living organisms, in the process of photosynthesis, find it slightly easier to use the lighter carbon-12. This means that carbon derived from organic sources, like the gases from volcanoes that cooked ancient coal deposits, or the methane released from decaying swamps, is rich in the lighter isotope. When the Wrangellia eruptions pumped a colossal amount of this light, organic-derived carbon into the atmosphere, it changed the global ratio of carbon-12 to carbon-13. This change was recorded in any rocks that were forming at the time, particularly in limestone and in the fossilized organic matter within the layers. When geologists analyze the isotopic signature of the rocks layer by layer, they see a dramatic negative spike in the carbon-13 signal right at the beginning of that dark, wet chapter. This chemical fingerprint is the same all over the world. It is the universal timestamp of the catastrophe, allowing a scientist in Vietnam to correlate a rock layer with one found in Germany, knowing they are looking at the exact same moment in planetary history. Piecing this story together is not simple. In many parts of the world, the pages of this chapter were torn out by millions of years of subsequent erosion, creating a Carnian gap in the record. No single location holds all the clues. The story is a mosaic, painstakingly assembled from thousands of different outcrops on every continent. A global collaboration to read a single epic chapter in our planet's long and dramatic life. Having read the story of the Great Rain in the archives of the rock, we can now place it in the planet's larger library. The Carnian pluvial episode, as dramatic and transformative as it was not an isolated event, sprung from nowhere. It was a single intense chapter in a much longer epic of planetary change. The Earth's history is not a steady linear progression. It is a story of cycles, of long, slow rhythms of warming and cooling, of wet and dry, all driven by the deep and patient forces of geology and astronomy. When we look at the whole of our planet's 4.5 billion year history, we see that its climate has oscillated between two primary states. The first and most common is the hothouse state. This is a world with little or no permanent ice at the poles, with higher sea levels and a thick atmospheric blanket of greenhouse gases. The second and rarer state is the icehouse, a world like our own, with significant polar ice caps and lower levels of greenhouse gases. The entire Mesozoic era, the age of dinosaurs, was a hothouse world. The Carnian event was therefore not a transition from an icehouse to a hothouse, but rather a violent and peculiar fever that broke out within an already hot world. What drives these immense slow cycles? One of the great drivers is the dance of the continents themselves. The supercontinent cycle, the slow gathering and dispersal of the Earth's landmasses over hundreds of millions of years, is a fundamental engine of long-term climate change. When continents are gathered together, like in Pangaea, ocean circulation is simplified, vast arid interiors are created, and the climate is one of extremes. When continents are scattered, as they are today, a complex network of ocean currents distributes heat more evenly around the globe, and climates are generally milder and more varied. The very act of a supercontinent breaking apart is a trigger for immense volcanic activity. As the strained crust finally rips open, the Carnian pluvial episode can be seen, in this grand perspective, as one of the first great convulsions of Pangaea's long death. It was a symptom of the internal heat that had built up beneath the supercontinent, finally breaking through, heralding the beginning of the rifting that would eventually open the Atlantic Ocean and create the world we know. The Earth, then, is a single, interconnected system. The slow churning of the mantle deep within the planet dictates the movement of the continents on the surface. The arrangement of those continents dictates the patterns of the oceans and the atmosphere. The chemistry of the atmosphere, in turn, dictates how much heat the planet retains, and the rain that falls from that atmosphere slowly weathers the continents, influencing the chemistry of the oceans, and eventually, the composition of the rocks that will one day be subducted back into the mantle. It is one great looping conversation between rock, water, and air, a conversation that takes place over a time scale that dwarfs our own existence. And so, the story of the Great Rain gives us a profound sense of perspective. It is a reminder that the stable, temperate climate that has nurtured human civilization is not a permanent fixture. It is a specific state, a chapter in the planet's much longer story. The Earth is a dynamic and restless entity. Its history is not one of placid equilibrium, but of long periods of relative stability, punctuated by moments of dramatic, system-wide upheaval. Just as our own lives are governed by the familiar cycles of day and night, of the moon and the seasons, the planet itself breathes to a much slower and more powerful rhythm. The 2 million-year reign was one such breath, a hot, humid exhalation that remade the world. It is a humbling thought that our own moment in time is just that, a moment, a single snapshot in a story of constant, deep, and unending change. Our journey through the fire and water of the deep past is now drawing to a close. We return to the world remade, to the quiet aftermath of the storm. The final legacy of the Carnian pluvial episode was not the roar of the deluge, but the profound silence that followed it. It was the silence of a world emptied of its former masters, a quiet canvas upon which the future could be painted. For the first time in generations, the sun would have been a constant presence in the sky, its light sharp and clear. The air itself would have carried the memory of the long rain. Imagine the scent of the planet, an ever-present petrichor, the rich, clean smell of rain on dry earth, a fragrance that would have lingered for centuries. It would have mingled with the scent of the vast, damp floodplains, the decay of the old fern world, and the sharp, aromatic resin of the new conifer forests that were marching across the continents. This new world was one of quiet beginnings. In the silent forests, the first dinosaurs were diversifying, their footsteps soft on the damp earth. They were not yet the giants they would become, but the potential was there, encoded in their efficient bodies and their relentless adaptability. They were the heirs to an empty kingdom, and they were taking possession of it, not with a great conquest, but with the patient inevitability of life filling a void. In the seas, an even quieter work was underway. In the clear sunlit waters, the tiny coral polyps were patiently building. Millimeter by millimeter, they were laying the foundations of the great reef ecosystems that would dominate the oceans for the next 230 million years. And in the dark of the night, beneath the canopy of the new forests, the first small mammals would have scurried, their warm blood and keen senses, a different kind of evolutionary experiment, biding its time. The story of the Great Rain is, in the end, a story of profound resilience. It is a testament to the tenacity of life, its ability to endure even the most extreme and prolonged crises. The planet threw a challenge at its inhabitants, a test of fire and water that lasted longer than our own species has existed. And life, though battered and transformed, met that challenge. The world was not destroyed. It was reset. The crisis was a gateway, a violent passage from the old world of the early Triassic to the new world of the Mesozoic. As we look back from our own moment in time, we can see the echoes of that ancient reign all around us. They are in the pines and cypresses that stand on our mountains. They are in the coral reefs that grace our tropical seas. And they are in the very dominance of the dinosaurs that so captures our imagination, a reign made possible only by the emptying of the world. The Earth is its own historian, and the story of this event is written in a thin, dark band of rock. It is a story that reminds us that the world is a book of many chapters, and that even the most destructive of endings are, from the perspective of deep time, simply the prelude to a new and unexpected beginning. Our own time will one day be a thin layer of rock. What story will future geologists read in the strata of our age? What silence will follow our own noisy chapter? The thought is a humbling one, a final quiet question to ponder as our own journey comes to an end. And so our long travel through the deep past finds its gentle conclusion. The echoes of that ancient endless reign now fade, returning to the silence of the stones from which they came. The world we have visited is gone, buried under more than 200 million years of time, a lost landscape of memory. But the great, slow cycles of the planet continue, the patient rhythm of rock and water and life. A heartbeat so slow we can barely perceive it. The story of our world is one of profound and constant change, but also of incredible resilience. In every forest, in every reef, in the very air we breathe, we are surrounded by the legacy of survivors. As you settle into the quiet of your own space, let the vastness of this story be a comfort. Let the thought of a 2 million-year storm make the gentle sound of a passing shower outside your window seem like a sweet and reassuring lullaby. The great dramas of the planet unfold on a scale so far beyond our own, and our own lives are a precious, fleeting, and beautiful moment of calm in the midst of this grand cosmic story. The questions we have pondered together can now be released into the quiet of the night. There is no need for answers. There is only the gentle call of rest and the turning of the world, carrying us softly towards a new day.